Good afternoon. I'm Bryan. I'm a senior in biological engineering in the Anderson and Langer labs. I'm here with my mentor, William, who is a PhD candidate, and together we'll be presenting on our Midnight Fibrotic Dragon. So one area that the Anderson lab is interested in is medical devices and implants. Medical implants exist on a large spectrum and have been used to treat a large range of diseases. So just a few examples up here are pacemakers, which are able to send electrical signals to the heart in order to treat heart arrhythmias, and drug depots that are able to release a scheduled dose of any drug without the need for repeated injections. Implants have also been used for structural and cosmetic reasons, for example, with breast implants. Once the implant is inside the body, you would hope that a helpful device would be accepted with open arms and welcomed by the immune system, but unfortunately, it is not. So when the body encounters an unfamiliar object, it begins something known as the foreign body response or fibrotic response. During this response, the immune system will recognize the implant as foreign, it'll attach to it, and it'll begin attacking the implant. It'll also recruit other cells to deposit extracellular matrix and collagen onto the implant, essentially walling it off from the rest of the body. This process, known as fibrosis, evolved as a response in order to protect the body from foreign objects to stop them from causing further harm or infection. However, as you can imagine, this is a problem for our medical implants. So using our earlier examples for pacemakers, this fibrous encapsulation can prevent pacemakers from sending their electrical signals. It can prevent these drug depots from releasing their drugs. And for soft devices, such as breast implants, it can actually cause complete rupturing of the implant. So therefore, we aim to prevent this fibrous encapsulation by creating a polymer coating that is able to tell the immune system that the implant is safe and prevent it from recognizing it as dangerous. And by doing so, we hope to improve the function and the longevity of medical implants.
So how are we actually doing this? Our approach is to take some immunosuppressive chemicals that we've discovered in the lab and actually transform these into a solid state coating that we can then apply onto the surface of different medical implants. And the effect of this is that we can actually generate essentially immunosuppression upon contact and effectively reduce the safety concerns that you have associated with systemic immunosuppression. And in order to test this, we generated a library of different types of polymer coatings and put them onto different implants. And then we implanted them into mice for at least a month before we explanted them and analyzed the tissue that ends up depositing on the surface. And long story short, you can take something like this and turn it something more into this. So as you can see with our lead candidates, we're actually able to dramatically reduce the amount of fibrotic tissue that forms up on the surface on the implant, allowing us to ensure a clear line of communication between the implant and the patient's body. And for some sort of technology transfer or a scientific publication, this before and after image that we're illustrating here is kind of what we really want to see. But what we found kind of interesting was actually this image that we captured and ended up being the image award contest winner. And what we see here is actually this dynamic fibrotic process in action. This partially fibrosed implant that we're able to capture shows these billowing cloud structures, which are actually swarms of immune cells that are sort of the first line of defense that are crawling along the surface of the implant, and it's flanked by this dragon-like structure that's actually collagenous tissue and newly formed blood vessels that can bring further immune recruitment to the implant site. And so with that, we hope that you guys enjoyed a little snapshot of the work that we're doing upstairs. And we want to thank the people that made this possible, including our collaborators, our professors, Dr. Robert Langer and Dr. Anderson, and then of course our funding sources, and of course the Koch Institute for providing this great environment to do this work.